chair of the IoT working group, Yasunori Owada from NICT. But I'm unfortunately I cannot go to the conference venue, so I remotely chairing these sessions. So these sessions we have firstly I will explain about the IoT working groups, and this working group is the pub to sharing the and also promoting the IoT research and development and the deployment of future society goals. So the IoT is now key technologies of this kind, depending on the digitalization society. So this working group is a forum for discussing and collaborations on IoT platforms, infrastructure, and services. So if anyone who have some experiments about the related work of IoT, and please come here and introduce your work or in this working groups. So this working group chair and co-chair is listed here. And today we have three presenters we invited. And the first presentations is from Nectec Thailand, Natchpong Hatti. And the second one is from Kanazawa University, Ruidong Lee. And the third one, I will present some recent activities about the disaster response use cases. Okay.
Good morning, everyone. My name is Natchpong Hatti from the National Electronics and Computer Technology Center, or NECTEC, under the National Science and Technology Development Agency, Thailand. Today, I'm pleased to present our work entitled An Energy Sharing Solution for Off-Grid Rural Communities, Sustainable and Ongoing Deployment in Thailand and Southeast Asia. And this work is supported by the Asian IVO project, Smart Energy Sharing and Management Devices for a Low Carbon Society, funded by NICT Japan, with partners from Thailand, Laos, Myanmar, Cambodia, and Japan. We also gratefully acknowledge the Energy Regulatory Commission of Thailand, or ERC, for supporting the earlier development of the energy sharing devices. For the contents of my presentation, starts with the background and challenges of independent off-grid systems in rural areas. It then introduces our proposed solution, the energy sharing devices, followed by our vision toward a smart energy sharing network. Finally, I will conclude the presentation. Some areas in Thailand. Some areas in Thailand and in other ASEAN countries still have no access to national electricity grids. In Thailand, many of these areas are designated as a reserved forest, where public utilities, including grid infrastructure, are not permitted. For our ongoing project, one of the targeted area is a school located in a reserve forest area in northern Thailand, near the Myanmar border, as shown on the left slide. The main energy sources for the school and surrounding community are micro hydro power systems and multiple independent off-grid PV systems. The micro hydro power systems supply electricity not only to the school but also to thousands of households, and due to limited water capacity, they often experience power shortages and fluctuations. In this presentation, I will not go into the technical details of the micro hydropower systems. For the school itself, electricity is mainly supplied by several off-grid PV systems installed on the rooftops. As shown in the picture, uh, there are at least 7 independent PV systems. For simplicity, the diagram illustrates only 2 of them, as shown on the right. Each PV system consists of PV panel, PV charger, inverter, battery module, and local electrical loads. Using multiple independent off-grid PV systems offers important advantages such as low voltage and safe operation, typically around 48 volts, and the use of widely available components that can be maintained by local technicians. However, a key limitation is that energy cannot be shared among these systems. As a result, some systems may have surplus energy, while others experience shortages, leading to energy waste and inefficient utilization. Our project addressed this challenge by introducing energy sharing device, which I will explain in the next part of the presentation. From the background I just explained, the school operates multiple independent off-grid PV systems. Here, we compare PV capacities, daily generation, battery size, and load demands for 5 representative systems. Some systems, such as System 1, 3, and 5, generate more energy than they can store or use during the daytime. This excess energy is simply wasted. At the same time, System 2 and 4 experience energy shortages. When we sum up the surplus energy, the total wasted energy is about 25.8 kilowatt hour per day. That corresponds to roughly 9,400 kilowatt per hours per year, or about more than 40,000 Thai baht, or around 1,400 USD annually under conservative assumption. This clearly shows that the main issue uh, is not insufficient generation, but the lack of energy sharing between systems. If this wasted energy could be shared, the estimated payback period of the energy sharing devices would be only 1 to 2 years. If we try to solve this problem using centralized or AC coupled approaches, several practical issues arise, especially in rural areas. First, there is a lack of local operators. The centralized system typically require external experts for operation and maintenance, which are not available locally. Second, the maintenance response time is very long. When failures occur, some systems may remain offline for extended periods. Third, access is difficult. These communities are located in remote areas with poor transportation, making regular maintenance challenging. As a result, the operational cost becomes very high due to travel, logistics, and specialized labor. Because of these constraints, centralized and AC coupled solutions are often impractical for rural off-grid communities. Therefore, using energy sharing devices or ESDs emerges as a practical and attractive alternative, which avoid centralization while improving system level efficiency. This slide shows the proposed method energy sharing device. ESDs operate without interfering with existing systems, allowing each PV system to remain independence while preserving simplicity, safety, low cost, and ease of maintenance. Two types of ESDs are developed. The first, DC to DC ESD, enables bidirectional energy sharing between nearby battery-based systems, as shown on the left side and highlighted in orange. The second is the AC to DC ESD, as shown on the right side of the picture. AC to DC ESD supports unique directional energy transfer from AC sources such as distant inverters or micro hydro systems to charge the batteries. In practice, uh, only the required ESD types are deployed at each site, making the system flexible, scalable, and adaptable to real-world conditions. This slide briefly introduces the key technologies used in the ESD. We consider two main architectures depending on the energy sharing scenario. The first, on the top, is the DC to DC ESD, which is based on a dual active bridge or DAB DC to DC converter. This architecture enables bidirectional power transfer between DC bus from the right, from back, for example, from left to right and from right to the left, making it suitable for direct energy sharing between battery systems. The device integrates fast analog and digital control communication with the external devices such as battery system, local monitoring, and a high frequency isolation transformer here for electrical safety. The second is the AC to DC ESD designed for energy transfer from an AC source, such as a micro hydro system or a distant inverter. It consists of a two-phase interleaf boost converter for power factor correction, followed by a DAB converter for isolated DC conversion and battery charging. This architecture shares the same protection, control, communication, and isolation concepts as the DC to DC type. This slide explains the energy sharing logic used in our offline methods. The key idea is very simple. Each ESD, each ESD makes decision locally based only on SOC or state of charge of the system. It connects with without any communication or central controller. On the left side, this is the logic for DC to DC ESDs. We divide the SOC into three regions: high, medium, low, or HML. When a system's SOC is high, it's allowed to send energy, but it will not receive energy from others. When the SOC is in the medium range, both sending and receiving are visible. This zone acts as a buffer region to avoid unnecessary power oscillation. When the SOC becomes low, the system disables sending and enables receiving energy from other systems. Energy transfer happens only when one system is in the high region and others is in a low region, like this picture. This simple rule ensures stable operation and prevents conflict even without communication. On the right side, this logic is applied to the AC to DC ESD. In this case, energy is taken from an AC source only when the battery SOC drop below a predefined threshold. And this slide shows the actual electrical system configuration at the school after installing the energy sharing device. Each blue circle represents the independent off-grid PV system, and they are located in different buildings across the campus, such as gymnasium, kindergarten, and teacher residence. On the left side, system 1, 2, and 3 are located close to each other. Therefore, we use DC to DC ESDs between these systems. On the right side, system 4 and 5 are located farther apart, farther away. In this case, AC to DC ESD are used. And this slide shows how the AC to DC energy sharing device is integrated into the school's real system. The energy sharing device and related accessory parts are highlighted in green. Importantly, battery management remains local and all systems operate autonomously. If the ESD is disconnected, each off-grid system continues to function normally without any impact on its original operation. And this slide shows about the DC to DC energy sharing device at the school system. The energy sharing device and its related X-ray part are also highlighted in green, as shown in the next slide. And this slide shows the actual system configuration in our DC to DC ESD field experiments. Redraw to clearly illustrate the current flows in the system. Here, IPV represents the output of the current of the PV charger. I load is the inverter input current, which we consider as the load current. IBAT denotes the battery charging or discharging current, and I share is the energy sharing current flowing through the DC to DC ESD, either to or from another system. In this case, a nearby system equipped with 48-volt lead-acid battery. On the right side of the slide, you can see photos from actual field deployment showing both DC to DC and AC to DC ESD units installed at the school. This slide presents the measure energy sharing waveforms of the DC to DC ESD during field operation. On the top traces, the battery voltage VBAT remains almost constant at around 51 volts. The PV current IPV is also relative constant. The key waveform is I share here. In the left plot, I share is positive value, showing the surplus energy is exported to the neighboring system. In contrast, the right plot shows I share negative value corresponding to receiving energy from other system. Meanwhile, the load current I load remains stable, which confirms that local loads are not affected by energy sharing. Note that I load is a 50 Hz AC waveform. Therefore, when observed with a time scale of 2 seconds per DIV, it appears as a band rather than a distinct sinusoidal waveform. Finally, the battery current IBAT adjusts smoothly, compensating for the share power without abrupt transients. Overall, these results confirm that ESDs enable control bidirectional energy sharing while maintaining system stability and preserving normal operation of the original off-grid system. And this shows how the AC to DC ESD configuration used in the field. And I share is here is only one directional power flow for the AC to DC ESD. And this slide shows the measure waveform of the AC to DC ESD. The concept is similar to the DC to DC ESD, but here the power flow is unidirectional, as in the sharing current I share here is only positive value. This slide summarizes the testing results and key specifications of the developed ESDs, including both DC to DC and AC to DC types. Both ESDs are rated at 3 kilowatts. Both ESDs comply with the safety and electrical standards as listed in the table. The photo on the right shows the actual hardware used in the field deployment. And this slide illustrates limitation of the current offline energy sharing approach and motivates our future work toward online control. On the left, we show offline energy sharing. In this approach, the energy level HML represent only the battery state of charge or SOC. Each ESD make the decision locally based on solely on the system it is connected to, without communication with other systems. As a result, even when system 3 has a high energy level and system 1 is critical low, energy transfer may not occur because the predefined sharing conditions are not satisfied. In this example, system 2 is located in the middle, but it neither require energy nor enables energy forwarding. Consequently, all ESD remain idle, leading to delay or inefficient energy utilization. In this situation, system 1 may soon experience a power shortage while system 3 continue to waste surplus energy. On the right, we illustrate the concept of online energy sharing, which is part of our future work. Here, the energy level can reflect overall energy availability, including both energy production and utilization. System exchange information through an online platform, allowing energy to flow dynamically from high energy systems through intermediate system and to the low energy system here. This comparison highlights that while the offline approach is simple, robust, and communication free, it sacrifice optimality. Offline control is suitable for two system configuration, but as the number of systems increase, online coordination becomes much more effective. And this slide presents our future works towards a smart energy sharing networks, extending the current offline approach to an online coordinated system. At the bottom, we show the energy sharing network where each ESD is equipped with an ESD32 based controller. The ESDs communicate locally using LoRa or RS485 or CAN-bus, which are suitable for long distance and reliable communication in rural areas. All ESDs are connected to a gateway which aggregates local data and communicates with the cloud via Wi-Fi when internet access is available. At the cloud level, we perform calculation, monitoring, and smart energy management, including energy balancing, decision, and remote control commands sent back to the ESD. Because the data volume is small, a lightweight cloud platform such as Google Sheets is sufficient for implementation and deployment. With this architecture, energy sharing decisions are no longer based on only on local SOC. Instead, systems can share global information, allowing energy to flow more efficiently across multiple systems. And to conclude, we demonstrate energy sharing device or ESD as a practical solution for rural off-grid communities. We design and deployed both DC to DC and AC to DC ESDs in real field conditions, showing that energy sharing can improve energy utilization while remaining non-intrusive to existing systems. The approach preserves the key advantages of small off-grid systems: safety, simplicity, and low cost, which are essential for the remote areas. Finally, we identify limitation of offline energy sharing and outline future work toward a smarter online energy sharing network. Okay, thank you for your kind attention.
Thank you very much for your presentations. And unfortunately, I was not in the venue. So, if you do you have any question and comments from the venue? Please use the microphone and ask him.
Hi, My name is Shinji Shimojo from Aomori University. Thank you for the presentation. I live in Aomori. It's some rural area in Japan, and even in Japan, in the deep mountain, we have off-grid sites. So your research is very interesting. So my question is, even I think you don't use the communication right now, but you have data from the uh, system. How do you get that data right now?
Okay, thank you. It's very good question. Right now the question on the in the table, right? We just
Yeah.
interview the operation people there. Just interview that how many how much of the electricity that they use each for each day or something like that daily. Just interview. So the data may be not so accurate because our system is offline recently.
Okay. So
So
there's no, I think, local logging system or so.
sorry.
Uh, is there, local logging system with the,
Yeah.
yeah.
For the previous project, we don't have any data logging.
Okay. Okay.
However, for the future work, yeah, we improve the system to be the online system. So I think for the next for our future work, we can see the accurate data. Like actually, recently we are working on this. We upload the data to the Google Sheets.
Okay. Thank you. And my next question is, how far the ACDC site is located?
In at the school, for the AC to DC around several meters.
Okay. It's not
Yeah,
so far, I think.
not so
Okay.
far. However, for the micro hydropower system, the the distance should be in kilometers. If we can receive the AC source, yeah, is okay. We can use this energy.
I see. Okay.
Okay,
And
thank you.
in your future project, I think this is you say school.
Yeah,
So anyway, I think they need internet connections. So maybe
yeah,
you may use the system like Starlink or so, and distribute the internet as well.
yeah. That is a one alternative solution
Yeah.
for the network for the communication network. However, recently at the at the other side of our project, we use we use the outdoor router to receive the mobile network signal.
Okay.
Yeah,
I
and
see.
we use the Wi-Fi send the signal down to the village or something like that.
Okay. So mobile is available.
Yeah, that's
Okay.
just available on the top of the mountain. However,
I see.
uh, in the in the village, in the household, they cannot receive this signal. So we need to pick the signal up on the top of the mountain, and then we use Wi-Fi send the signal down to the village.
Okay. Thank you. Thank you
Okay,
very much.
okay, thank you,
Very
thank you.
interesting.
Okay, do you have any other questions and comments?
Thank you so much. I am Dr. Mutahharul Islam from United International University, Bangladesh. So actually, I am also working in this sort of, work by our students. So you see, are you, trying to replace the, smart meter by your, ESD, that means energy sharing devices? Because
Sorry, please come again, please.
so actually, this sort of, energy sharing devices, it is actually, it can be used by using the existing smart meter, you see.
Yeah, 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 yeah.
So are you
Uh,
proposing a new device, IoT based devices for the, off grid, rural communication? Because nowadays in the village also, the electricity supplying companies, they are providing smart meter. So why not we will be using the existing meter? Why do you
Actually,
need another device to be?
yeah. Okay, thank you for your question. For the ESD, they use for also sharing energy. However, for I would say for the electrical parameter, right? In this case, we also use some commercial power meter to combine with the system in some case, just depending on the areas. And in some areas that they use the inverters that we can communicate with the inverter, that's which is the commercial inverter, and we can communicate with. We can collect some data from the inverter as well. So in this case, we don't need additional power meters. However, commercial power meter also one of our methods to measure the power or the voltage or current of the systems. Is
Okay, another thing is you
okay.
see, I have seen in your architecture, you have
Okay.
used different, component for AC to DC and DC to DC, right? And some
Yeah,
of the
yeah.
component also represent the, battery. So you mean you will also store the energy in battery
Oh, thank you.
to reduce the wastage?
Okay, let me go back to to where maybe here, right?
Yeah, here this slide, right?
Yeah, actually,
No,
the
just
power
the, the
can be
previous one, next or previous, please.
this one.
Yeah, this one, right?
Yeah, actually, we can how to say we can change the energy sharing modes, such as if we want to store the energy to the battery, yeah, it's okay to do that. However, in some case, we just bypass the energy directly to the other inverters. This is also, for example, if this one has a high level of energy, right, for the down the below one, right, below battery. And in this case, if we want to charge this battery, we can adjust the operating mode of the DC to DC ESD here to charge the battery. However, if we want to bypass the energy directly to the load, we can change the operating mode, such as I I call load follower, something like this. Energy will flow from this battery through the DC to DC ESD and will not charge to the battery, just directly go to the load like this. It's no need to store to the battery, just share the necessary energy. It is
Okay, my last question is actually, you see, in your proposed, future architecture, you are using the LoRa, CAN, and RS485. These are the communication protocol, right?
yeah this
Among
just
the
this.
different ESDs. So in your proposed implementation or the prototype implementation, you have also mentioned that you are using ESP32, right?
Yeah.
So which specification of ESP32 actually you are trying to use? Because LoRa, RS485, and CAN. So or the three protocols are applicable for ESP32, or you are adding some extra module with the ESP32?
Yeah, actually, ESD, we have done the prototype already. We just want to equip just a small IoT modules. So ESP32 is very, I'll say, light, very light controller and enough for sending the energy data of this ESD. So we use this, and it's very how to say, very simple and don't waste the time too much or something like that. So we use this one, and there are so many ESP32 modules that we can decide to how to say, just like we can decide to communicate with LoRa or RS485 or can we can use the TSM32, which is buried in the ESDs already.
Okay, thank you. I visited NICTEC in 2009 in the TAIN workshop. So it's wonderful to, have your presentation today. Thanks a lot.
Okay, thank you very much.
Can you see the slide? Actually, I just introduce the outline, and then I will introduce the definition and property of metaverse. Metaverse, as you know, it's a digital world that integrates the physical and the virtual space, and it is characterized by immersive reality, super space and time, sustainability, interoperability, and scalability. So this is the trends of the metaverse development. Metaverse keywords occur at a slow crash. This is a fiction published to 1992. And Digital Twin occurred 2002. And the Second Life is a game occurred 2003. And Bitcoin and blockchain occurred 2008. And then NFT occurred 2012. And then Decentraland and Pokemon Go 2015 to 18 and 2021, Facebook changed its name to Meta. And then Apple Vision Pro occurred 2023. So this is a key technology of the metaverse. It's a multidisciplinary area, includes the extended reality, blockchain, digital twin, network and communications, artificial intelligence, and cloud edge computing. For the applications of the metaverse, we can see that there are virtual socialization office. So for example, create avatars in the metaverse to interact with different users. And for the industry, use technology such as digital twin to simulate the development of new products in the virtual environment. And for the entertainment and games, they offer virtual games and virtual realities, esports, and others. For the health care, the simulated medical scenarios for surgery, disaster diagnosis, and treatment. For the virtual economy and asset, both digital real estate and concurrency and digital art can be bought, sold, auctioned, and gifted. For the future metaverse, there are at least 4 research directions here. The first one is a diverse access method. There are many access methods for the metaverse and privacy information protection and a unified indicator and standards and the integration with advanced AI technology. So this is the reason why I introduced the AI, genetic AI here. For the metaverse architecture, in the physical world, there are users, physical environment, physical goods and service. We can create the metaverse component in the virtual space. For example, the users correspond to the avatars and the virtual environment correspond to physical environment, and the virtual goods and service correspond to physical goods and service. And then those components can be composed to the metaverse world, sub-metaverse, and then provide a service to the end users. This is the infrastructure. We use the communication, computation, storage, enabling technologies, and ER, extended reality, SC, HCI, and AI, and etc. And as for the service providers, there are many physical service providers and virtual service providers, and then metaverse. Actually, currently the metaverse services are mainly provided in the cloud. So this is the existing ones. We collect the data from the end, and then create a digital twin and the metaverse service in the cloud. This is the current metaverse architecture. Here, we went towards the future society usage. We try to enable the users, and the users can create their own metaverse. And the end user can also provide their servers, their redundant servers for the metaverse creation. So we put the decentralized intelligent metaverse vision as our research vision. And you can see in this part, for the sub-service physical provider, they can provide their own base station, own servers for the metaverse creation. and for the service provider, each of us can create the digital twin and provide digital twin service or provide a metaverse service. This is anybody can provide the physical infrastructure or physical server, and any of us can provide the digital twin service in the future. This is what we are imagined. So we also need to enforce intelligence to this metaverse. To realize this vision, there are some challenges. For the challenges at the from the viewpoint of the sub-physical providers, we need to design the collaboration method because, for example, I have a server I want to provide for two others. We need to collaborate with each other. Many of us, we need to collaborate with each other. And it is expected to increase bandwidth, low latency, and more computation power. And also for the sub-service provider, we also, for example, I have some digital twins, and I want to provide some service. How to enable this happen? This we need to in collaboration method, and then expect a flexible and a high quality metaverse service. For the sub-service providers, the collaboration method, how to enable the collaborations among the decentralized physical devices. For here, we propose a computation-oriented network. And for the expected increased bandwidth, low latency, and more computation power, the how to predict the traffic with the metaverse service is important. Here we propose traffic prediction in metaverse and traffic prediction with network digital twin. This is our publication here. If you are interested, you can try to read the papers for the IEEE network, JSOC, and IEEE network. So today I will mainly introduce our work on the sub-service provider, the collaborations, how to enable the collaborations among decentralized metaverse or digital twin service providers. Here we propose a decentralized digital twin network. And we also, for the expected flexible and high quality metaverse service, the main question is how to enhance the service quality of the metaverse users. Here we propose a task-oriented semantic communication in large multimodal models based big networks. So here I will first introduce a decentralized digital twin network here. First, I introduce digital twin. Digital twin is create virtual replicas of physical objects. First, digital twin history is a set of the simulators were used to train the astronauts and simulate aircraft's components in Apollo 13 mission of NASA. And current applications include smart factory, intelligent transportation, aging simulation, and etc. It has merit on the dynamic city, real-time, bidirectional, and high fidelity. So this is created this physical twin and create digital twin and collect the data and create the digital twin and then enforce decision to the physical world. In the simulation or in our implementation, we use NVIDIA ISAC sim. Actually, for the current computation infrastructure of digital twin, essentially decides the prediction performance. And networking and data resource quality affects the fidelity of the virtual replicas. And the computation power are needed for the running accurate prediction model. And related work focus on actually this is a component scale digital twin. This is only part of the device. And also there are system scale digital twin, networks or assembly line. And the question is how to support a large scale digital twin, for example, smart cities and Earth and etc. This is our main mission. So there is a gap. Few works tackle large scale generation, robust operation, and secure sharing simultaneously. To solve this problem, and there are limitations for the existing digital twin network. There are low scalability and poor fault tolerance and data signal. just so you can see that we put the cameras at the edge and then connect the data and then transmit to the cloud server and then create the digital twin. This is currently what we are doing for the decentralized digital twin. However, when we consider decentralized digital twin, and we first here we propose a decentralized digital twin networkers here. There are a new paradigm enabling highly scalable, trustless, and shareable digital twins. There are three layers: digital device layer, digital chain layer, and the virtual platform. Oh, sorry, I cannot show the figure here. This is a centralized whole view figure here. Actually, the basic considerations we use blockchain to validate the digital twin generated at the edge. We need the edge device. We need the edge device to connect the data and generate the digital twin, and then use the blockchain to validate the data as a digital twin, generated digital twin, and then tokenize the digital twin, and then make a digital twin shared among the users. This is then the service provider can conduct the tokenize the digital twin and then get the connected digital, aggregate the decentralized digital for the large scale applications. However, for the decentralized digital twins, there are problems. There are advantages and also problems. Advantages, there are actual low latency and less data transfer and verifiable ownership and trust and fault-tolerant consensus and multi-stakeholder sharing. There are problems, for example, at the edge device. There are many edge devices. If edge device corrupted, or if the edge device deliberately provided the false digital twin, and this is a problem. So we use the blockchain to assure to validate those digital twins, and I use the blockchain for the digital twin validation and tokenization. The figure here cannot be shown, and actually, for example, there are three cameras at the edge and connect the data, the same car, the same device, physical entity. For example, a car. Two of them say that this car is with a color of red, but one edge device said that this car is with a red, with a color of yellow. So we can see that we can use blockchain to use a consensus algorithm to determine this digital twin. The correct color for this digital twin is for this car is red. And this is our basic for the basic mechanism for the digital twin validation. So for the experimental setup, we have this environment 3 Jetson AGX and Logitech web cameras, and this is we use a camera here and then transmit this environment to the digital, create the digital avatar world here. So for the latency, we can see this is performance evaluation. We can see that the latency can be greatly reduced, and the data volume, because we do not need to send the data to the cloud for each time, and not send the streaming data. So we just process the data at the edge and create a digital twin at the edge. So the data volume will be, absolute data will be greatly reduced by 99.8%. Because we use the blockchain, so we need to evaluate the performance of the consensus algorithm. So the throughput for the digital twin digital twin blockchain, so we use throughput is 22 T transaction per second. So latency is around 200 milli per second per validation. So it meets the real-time traffic twin requirement. So these are application immersive metaverse. We just monitors in the university and then get the immersive reality. And this is we set the camera at the highway, and then create the real-time metaverse world in the omniverse, based on omniverse. This is our first work introduced here is propose a decentralized framework for digital twin network to improve the scalability and security. For second work, I will simply introduce our another three works. One is task-oriented semantic communication in large multimodal model-based vehicle networks. Because as you know that the large language model and this is large language model. This is large language model can only process the text. So large multimodal models can also process the image, audio, and video, and use encoder, multimodality encoder to translate to in token, and then input into the large language model. So, however, when we use it, for example, when we use it in the vehicular scenario, we drive a car and need a car driving assistant. So, if we deploy large language model and large multimodal models to the car, it will be infeasible because it costs much of the power and much of the computation resources. To solve this problem, we put the encoder at the vehicular side and the large language model at the cloud side. This is our one of our contribution. Another contribution is from here. Another contribution is, for example, we use the driving assistant. We just want to know, for example, what is the signal of the current signal for one cross ahead. So we just want to know that part of the semantic information. We do not need to the whole information. So we use a lightweight model semantic matching to extract the only task relevant image regions. Match the we just speech transmit our speech, for example, the signal at across ahead. Then it will directly transmit only the get this single part, and then input into the LLMs. This is to reduce the communication overhead. Use semantic matching or propose a semantic matching. This is our second contribution. For the third contribution, we use semantic importance map. Some part is important, some part based on our speech. Some part is important, some part is not so important. So we use the we create a semantic importance map to catch the important part of the figures or streaming videos and to input into the large language model. So this is our third contribution for this work. Of course, you can see that the accuracy will be improved by 33.1 per second, and the our proposal can achieve the better accuracy, answer accuracy. This is our second work I will introduce here. For the third work, for the digital twin for the disaster rescue, we propose a digital twin empowered post-disaster movable base station deployment optimization. Currently, when disaster happens, for example, earthquake happened in Japan, so we just put the data, put the movable base station randomly at the disaster area. So to solve this problem, we use a digital twin. First, use the drone to scan the create the disaster area, metaverse the virtual space, virtual scan the disaster area, and then create the virtual world at the metaverse area, here. Use the drone to scan the disaster area, and then create the digital twin in the local server, and then use the deep reinforcement learning to predict or to decide which place is suitable for the mobile base station place. So this is our another work application for the decentralized digital metaverse. So our proposal can achieve the better performance user coverage rate. We evaluated with the user coverage rate. So our proposal can get the best performance. For our last work on the task-oriented networking for agentic AI, actually this is the paper we just got accepted. For the current agent network, there is no method to here. There are so many agents in the future. How to make the agent to interact with each other? Based on the current internet, we can only realize such kind of interaction based on the IP address. You need to register your service at some place, and then others get your IP address. We currently use DNS or other method. So to solve this problem, we use the named data approach and the PubSub, and also on-path caching to make the agentic AI to interact with each other. For example, agent requests a context in request, and then also request a context update, request a context. For example, subscriber in request a context, request the this publisher to provide some service. For example, provide the predict the temperature outside. Then the publisher will get the temperature outside and then return it back to the subscriber. And this data can be cached at the local router or local local server. And then another subscriber can retrieve this kind of data from the close router or nearby server. And also another contribution, this is one contribution. Another contribution is we integrated the name-based approach with the model context protocol. For the local area, this is general purpose AI to interact with the local expert AI to use the model context protocol. This is our second contribution here. So this is our conclusion. So we propose a unified framework, propose an agentic AI system integrating specialized function agents and MCP-enabled expert interaction and task UN communications. This is our reference I introduced. If you are interested, you can get these papers from the public site. Thank you. Thank you very much.
Okay, thank you very much. Do you have any questions and comments from the audience? Okay.
Thank you, Professor Lee, for your wonderful presentation. Actually, I would like to add a few points. For example, you see from the physical layer, we have the virtualization layer and the application layer. So normally the camera based, you see the capturing of the image. Sometimes it, hampers the privacy. So the researchers, they introduce the sensor-based sensing of the physical infrastructure. But from your research, I see you are again proposing the camera-based, contextualization of the physical infrastructure. So if we consider it just like a cyber physical system, so if you reintroduce the concept of camera-based, monitoring. So do you think that it will not hamper the privacy? And definitely you have used the word semantic communication. It's a very good idea that, you are sending the meaning of the context or meaning, not the whole message. So would you please elaborate in that perspective? Because you see the technology is actually, it's just like a wheel. So I'll be very happy if you please explain those points.
Thank you for a good question. Actually, we consider our proposal actually is consider of the privacy. So actually, for example, in the current system, we use a camera at the edge and then take the videos and then send it to the cloud server. So the privacy will be violated, as you said. So we use so to solve this problem, we set the camera at the edge and then edge servers, and then we created the twin and process the videos at the edge. Process all the videos at the edge, created the digital twin, and then share this digital twin among the peers. So we largely reduces the leakage of the privacy information. We do not need to send the message, the videos, the whole videos through the networker and then to the cloud server. And this reduces the leakage from the video transmission, and also reduce the leakage, the privacy leakage from the cloud server side. This is what we did.
So what type of camera actually you are using?
Camera, we use the Logitech. In the experiment, we use the Logitech C920 web cameras.
Okay, so do you think that if we use the sensor-based camera, will it not be, more efficient, and at the same time it will also address the privacy issue?
Yeah, okay. Thank you. Thank you for a kind of comment.
Okay, thanks a lot. And just one more thing. You see, whenever we are actually, using a physical, infrastructure, and over the physical infrastructure, we are actually, providing, different type of application. So in most of the cases, you see the concept of virtualization or the virtual network, you see it requires a lot of bandwidth. So what about the complexity of that?
Yes, so this is what we are doing here. Most for the second work, we mostly try to send the semantics over the this also this. We not. I do not have the whole picture. Sure, actually we have a whole picture. We just use a camera to catch use of yellow to catch for the object detection here at this side, at the edge side, and then send the semantic information. Only send the semantic information to the server. For example, this car or USB car, and then yellow, black, and this is white, and this and the location, and send this kind of information, semantic information to the our omnibus, NVIDIA omnibus side. And then in the omnibus side, we use the already existing digital twin to map to create the virtual world. So this will greatly reduce the bandwidth consumption by our approach. We just send the semantic information here.
Okay, thank you, Professor Lee. Thank you once again.
Thank you.
Okay. Do you have any other questions?
Hello.
Okay.
I have one question. In the third work, you mentioned about the using digital twin in the case of disaster. And regarding the use of drones, how are they recording the video of the site? It is for the disaster preparation or after the disaster, for the disaster response?
This is for the after the disaster. after disaster, we need to deploy mobile base station at the disaster area. So where to deploy those base stations is the question we are researching. For example, the base station put a base station here or here or here. Which part is suitable? We can cover the most of the refuges. This is the question we are researching. So to solve this problem, we use a drone to UAV to further scan the disaster area and translate it to the virtual world. And then in the virtual world, there are buildings and then trees and then and can also simulate the deterioration. So then we try to use deep reinforcement learning to find a suitable place to deploy the base station, mobile base stations. This is what we did in this work.
Okay, thank you.
Thank you.
Okay. Any other questions? Okay, if no questions, let's move to the last presentations. Thank you very much for your presentations.
Thank you. Okay, thank
you. Okay. So I am the last speaker. And the time is a little bit limited, so I will briefly introduce my recent activities. So I am Yasunori Owada. I'm from NICT, and my presentation is Resilient ICT System for Disaster Response Agencies in case of large-scale disasters. So more than 10 years ago, or already 15 years ago, we have a big earthquake and tsunami in Japan, East Japan. And at that time, more than 22,000 people are passed away by this disaster. And at the affected areas, the mobile base stations are disrupted, and the communication disrupted, and people cannot use the mobile phones to. And this is the mobile service recovery. I'm sorry that some pictures are written in Japanese, but the March 11 is here. March 11 is here, and this is around 2 days after, and 8 days, and 40 days after. The x-axis, y-axis is shows stop the base stations, number of base stations. So after 2 days, the peak comes, and because of the stop of the electricity, increase the base station stops. So base station have the battery, but most of the base station only keeps 2 days batteries and or the power generators. So if the power outage exceed more than 2 days, they cannot continue operations. So in this figure, more than 2 weeks or several weeks to recover the communications. And 2024, March 1st, we also have the big earthquake and at the Noto Peninsula area in Kanazawa, near Kanazawa, Japan. And also, at the time, the base station communication disruption happens, and it takes more than several weeks to recover the old base stations. And because of the affected area is located in peninsula, so it takes time to get the entry pass to the affected areas because the road is damaged and there are no paths to reach to the affected areas. So it takes time to recover the infrastructures. So this is a mobile blackout area right after the disasters. And there are 4 main carriers in Japan, and each carrier stops the communication services after the disaster, earthquake. And it announced the recovery almost 2 months later after the disasters. So it takes time to recover us. And the disaster, this is a lesson learned from the Great East Japan earthquake, 2011, March 11th. So when the disaster, big earthquake and tsunami happens, the rescue teams like ground self-defense force enter the disaster affected area, but there are no information where which area is seriously damaged, and they just dispatch based on the populations of the cities. And at the time, this Paro area, this is a very small town, but it's seriously affected by tsunami, and most of the people passed away in these areas. But the population is very small, so only small number of people are dispatched to these areas. So after the information shared, and it's almost several days after, and they decided to dispatch a much large amount of people at these areas. So if the information sharing much earlier, they can rescue some of the people at there. So the information sharing is very important. But the currently in Japan, many agencies like firefighters, police, and self-defense force, they are sharing the information at the disaster affected area using the map and the whiteboard. It's a very useful way, but it's a little bit difficult to share the information timely. So we need to that digital transformation is very important for these areas. Okay, the time is a little bit limited, so I will skip some slides. And I will introduce the Sobo Web. This is the information sharing systems operated by the Cabinet Office Japan. And this system is started operating from 2024. But this one is a kind of a cloud systems. So people who are working in the disaster-affected area, the area may cannot may not be able to use the mobile communications, so they may not use this system directly. So that is the one problems. So currently we are now targeting to develop the cross-agency information communication systems for the disaster responders. We are now receiving the big fund from the cabinet office, which is called Cross-Ministerial Strategic Innovation Program, a promotion program, SIP. So our teams, these teams are developing the standard system for the information sharing among the multiple agencies. And our NICT developing the communication system for that people. So we are now developing such information and communication systems for the multiple agency, so which is called cross-agency information and communication systems, called CrossX XICS. So this system, the key point of this technology is which have the device have. Each device have the server functionalities and also the multiple communication ways, like mobile communications. Like each node have two mobile communication modules and different operators. And if there are satellite communications, and that communication lines are also trunked and expand the bandwidth automatically. And if there are no communications to the internet side, they can communicate each other, device-to-device communications, and then the data, server data is synchronized each other, and keep communications or information sharing among the nodes. That is the key point of these systems. So there is a video, but the narration is Japanese.
台風や地震などをはじめとした大規模災害が頻繁に発生しています。そのような災害においては、広い範囲で通信途絶地域が生まれ、現場で活動する実動機関の迅速な対応に支障が出るなどの課題があります。こうした課題を解決するために、大規模な災害等の発生によってインターネットへの接続ができなくなった地域も含め、被災現場で活動する災害実動機関同士の情報共有を可能とする機関横断情報通信システム、通称クロス X の研究開発を行っています。クロス X は可搬型装置に重層化した通信回線と情報処理機能を搭載しています。災害時の通信途絶地域でクロス X を活用することで、消防、警察、自衛隊などの実動機関が連携を行い、現場における災害情報の共有が可能となります。災害時の通信途絶地域でクロス X を活用することで、消防、警察、自衛隊などの実動機関が連携を行い、現場における災害情報の共有が可能となります。クロス X では、切れない技術と業務を止めない技術を開発しています。切れない技術では、重層化した回線のいずれかが接続していれば、自動でそれらを認識し、通信を継続することができます。また、複数が利用可能であれば、それらを束ねて容量を自動的に最大化できます。これにより、衛星、ハップス、 携帯電話網、光回線など、あらゆる回線を自動的に認識し、最大限に活用することで、現場における安定した通信を確保します。次に、業務を止めない技術を説明します。通信が途絶している被災地では、お互いの情報を得ることができません。クロス X は通信が途絶している場合でも、情報を本体に蓄積し、装置同士が近づくと、お互いの情報を自動で共有する機能を持っています。これが業務を止めない技術です。クロス X は装置間で情報をバケツリレーして共有し、装置単体でもシステムを継続利用できるようにします。これにより、通信が途絶している被災地域においても、現場内で情報共有を行うことができ、より円滑な災害対応を実現します。ここからは、通信が途絶した地域で、
Okay, the time is limited, so I stop the video. And this one is the first prototype of the Cross-X hardware. And it have the server functionalities and the multiple LTE modules. And it also have the Wi-Fi access point and the stations, and also the Wi-Fi Halo access point. This Wi-Fi Halo access point supports the mesh communications, so it can communicate each other only using the access point. So this Wi-Fi devices are for the device-to-device communications, and also the LTE is the communication to the cloud. And also there is several Ethernet connectors outside, and if the Starlink or other satellite communications and fiber communication internet access line is available, just plug the Ethernet cable. It automatically bundle that communication line and expand the bandwidth. And this one is a second prototype of the hardwares. And this is also the same functionalities. And but the battery is removed from the hardwares. And maybe various portable batteries are available commercially, so it can use for this one. So this hardware is for the mobile attached hardwares. So it can operate outside and wide temperature operations from the -40 degrees to the 60 degrees. And also, this is a current prototype of the much smaller hardwares. It can bring from using the drone and the mobile bicycle and also the robot. So we are now testing these hardwares at the disaster drill. This is a big disaster drill operated by the Ground Self-Defense Force. And we just provide the communication devices to them, and they bring it to the operation site and input the data from the smartphone. Then the information is synchronized to the multiple Cross-X node, and then the information is synchronized to the cloud servers. And also this is another disaster drill. It assumes that the mobile communication is not available. Then they can share the information at the coordination office to the rescue field. And in this experiment, we use Wi-Fi Halo and also the local 5G base stations to communicate each other. And this one is the prototype of the robot-mounted type of cross X node. So by using this one, the people, if the area which is difficult to enter, the robot can fast entry to survey and share the information, carry and bring it back to the information site. And the last one is recently we operated the disaster drill in Okinawa area.
3階からの侵入のみ、倒壊の危険あり、関連活動の準備と必要。赤ちゃんの声が聞こえるとの情報です。誰かいますか？3名で、ちょっと待っててくださいね。足が見える。OK。完了です。デッキは設置完了。今行きましょう。頑張りましょうね。すみません。すみません。
Okay, so usually this kind of disaster drill is planned by each individual agencies like Ground Defense Force or the firefighters drill and police office. So in such operations, there are no coordinations. So that's why we planned to do this kind of disaster drill and gather the multiple agencies and using these systems and evaluate the efficiency or effect. So evaluate these systems. So in this disaster drill, our system is used by the sharing the information with from the island to the mainland by using drone and bicycle and other devices. Okay, so the time is already passing, exceeding, so I will just skip the slides. So this is all of my presentations. I thank you very much for listening. And if you do have any questions, please. Okay, no questions. Okay, so already the time is exceeding.
Thank you so much. I still remember the devastating day, March 11, 2011. At that day, I was in Seoul, South Korea. So we experienced the wave and the tsunami after the great earthquake. So this is a very fantastic work. So actually, you were proposing some sort of, multi-homing technology, right?
Right.
Why the device has multiple, communication link, right?
Yes.
Okay, so I wonder, actually, you see wireless Wi-Fi and Ethernet, sometimes NFC, okay? Sometimes Bluetooth or infrared or LTE, right? So how it can be connected to satellite? And would you please explain in terms of fiber and satellite communication with the devices that you have introduced?
Oh, okay. So our systems are working as a routers. So it have the multiple communication devices or Ethernet devices. So if the device can be connected through the Ethernet cable, the communication line can be aggregated.
Okay, so you see, Japan is a developed country, so you can do many things whatever you like. But you see, I am from Bangladesh, and we experienced only 5.4 maybe Richter scale earthquake a few months back. So it creates a very chaotic situation. So what do you think, how we can develop a lightweight device that might be very much cheaper? For example, using the existing smartphone, because nowadays a smartphone is also, it has a power saving mode, and it can run for a longer time using the battery technology, right? So do you think it might be an alternative solution or lightweight solution, even if we use a smartphone and we have multiple, multi-homing tech? Already there are multi-homing in smartphone, right? What do you think of that?
Yeah, we also consider to use such kind of much commercial available devices to operating this kind of concept. But the smartphone itself is the operation system is managed by the Google Android and also the iOS Apple. So it is a little bit difficult to modify or customize the device level applications. So I give up to developing based on the Android or iOS, and we use the Linux-based operating systems to develop the systems. And our developed system is a software. The key technology is software, so we can install this software to the various hardwares. And if I'm currently using this kind of very small and power. Low power consumption hardwares like Raspberry Pi or much single board computers. So we can operate our software using this kind of hardware. So it depends how much the system cost is and how computation resources and other communication ways the system have to embed it initially. So it's a kind of trade-off.
Okay, thank you. My last question is how much actually it costs, the device that means used for the Cross-X?
Yes, the first, this one is commercially available hardware we just purchasing. This hardware is around, sorry for that, 10,000 US dollars. 1,000, no, 10,000 US dollar each. But this one, small one, we just purchasing the very reasonable price single board computers and the power bank and customize it. And the total cost is around 2,000 US dollar or something in total, only hardware. So, but if we our organization is a research institute, so we cannot do the service, so we just transfer this technology to the commercial company, and they can develop the products based on this technology. And I don't know how much the final price is, but the base hardware price is like that.
Thank you so much.
Hello, I have one questions. My name is Vishal. I'm from Nepal. I work in the Nepal police, and I am information and communication engineer there. And we basically are the first responder during the disaster, and the use of technology during the disasters come under my jurisdictions. So I want to just ask a question. In my country, when there is a disaster, just all the security agencies get together, just like army, police, fire brigade, they come together in the JOC. So just you are proposing to use the device. So all the agencies should have their separate this one XICS device in their office, or just they need to still come in the JOC for information sharing. And other is the information and that the one organization uses is quite different. The data format is quite different than the other. It's like the fire brigade use with different format for data information, and like the police and the army as well. So for the data format, how can we just make a uniform? Have you considered it here?
Okay. The first question is this is a country research part, still researching, but if we want to try to deploy these systems to the real agencies like firefighters, police, and others, it's a little bit difficult to deploy individually because this system is targeting for the large scale or disaster which need to coordinate multiple agencies. So in this country, our assumption is this system is deployed at the cabinet office in Japan, and then the big earthquake happens. The owner is cabinet office, but the location is installed in the, for example, the ground defense force, and they are continuously doing the training for the drill. So they commonly using these devices, and then what the big earthquake happens or big disaster happens, they carry these devices and share to the other agencies. This is one solution we are now considering, assuming. And another second question is the format. information sharing format. And now we are the CrossX itself have the WebGIS application server, and many agencies access this server to put the informations, and the information is have the uniform format, and that information is easily connected to the disaster information system operated by the Cabinet Office. So we just defined the format for these systems and deploy these systems to the Cabinet Office. And commonly we use the same format as at the Cabinet Office and these CrossX systems.
In the first version of the device, that I saw that the embedded battery operation was just for 15 minutes. So would that be sufficient for the operation?
Yes. This one is just for the UPS. So we need to put the outside battery.
If there is a disaster, then it will need to take at least 4-5 hours for the operation.
Yes. So this is the first prototype, and we just use very high spec CPU servers. So it consumes very powers. So we try to reduce the computation ability. And this type of single board computers, they can operate for 6 to 8 hours using the portable mobile battery we can purchase commercially.
So these are the server systems, and all the individual units that enter the digital data to the computer, right? Or do they still also collect the video footage from the sites, disaster site?
One more question, please.
There is also the drones and the other equipment. So do they also take the video footage of the disaster sites, or these only the audio and the textual data?
Any kind of data we can share. So they use a smartphone to access these CrossX systems, and they can put the voice data and the pictures and the videos and just put that information to the CrossX servers. Then the information is visualized on the map, and they can show easily show the information like this kind of map. Yeah.
Thank you. Well, just in my country, we are using the audio GPS and the UHF signals for similar type of communication, but it is very low end. We are just developing the systems ourselves. Thank you.
Yeah, thank you very much. Okay, so already 20 minutes passing, so I will close this IoT working groups sessions. So thank you very much for coming here and make our presentations.